Greetings, everyone. Welcome to my talk on big machines caring for little plants, how robotics is changing agriculture. Really excited to be speaking to you today. We're in a virtual environment, so doing recording here. This is a really exciting workshop with the Agriculture Vision Workshop as part of CVPR. Challenges and opportunities for computer vision in agriculture. So very excited to be talking to you today about some topics that are really quite dear and near and dear to my heart. A little bit about myself. My name is Chris Padwick. I work at Blue River Technology, and I've been there for the last 5 years. My main responsibilities at Blue River are the machine learning portion of our robotics pipeline. So I have a team of machine learning engineers that trains models that distinguish crop from weed. My background is in physics, actually, so the deep learning thing has sort of evolved as my career has evolved. In grad school, actually, we used to do something completely different. So imagine a high altitude balloon, a microwave telescope measuring the cosmic background radiation from the Big Bang. That's sort of like the largest scale things in the universe that you can measure. And now where you've got plants that are cameras that are 3 feet away from plants and trying to figure out how to kill them with a weeding machine and AI. So going from the very largest things to something a lot smaller. We really enjoy being outside. So we're in Tahoe and got a couple of wonderful kids and a great family. So very, very lucky to have that. And we try to spend a lot of time outside, as you can tell from our photos. I think farming is a really important problem for us to be working on as machine learning scientists and engineers. And it's kind of summed up in this graph pretty well. So if you look at something called the TFP, it's the total factor productivity. This kind of measures everything that you put in versus everything you get out. So this is really inclusive, and it's a very inclusive metric. And if you look at where if you're getting more out than you put in, that's obviously great. And to the extent that you get more and more out with being more efficient with what you put in, that's really the key here. So one thing that's really kind of scary about this graph is if you project the low-income countries out, you can see that there's this really big TFP gap. And the fix for this is we need to get more efficient at farming. We're doing okay, and we need to keep that rate of growth, matched there. And you can see that there's only a small gap on a concerning gap, but much smaller than there is on the lower income countries. What drives this? Well, it's population growth. We need to get more efficient at how we farm, produce more food, get more yield from the acres that we farm. That's why I think this is a really important problem that we need our best minds working on worldwide. This is a worldwide problem. If you look at how agriculture has evolved, say, over the last 10,000 years, there's been a number of kind of revolutions and eras. Initially, you had hand tools. Then in 1837, John Deere came up with a vastly improved plow, which caused its own mini revolution. And now I work for John Deere. Blue River is a subsidiary of John Deere, wholly owned subsidiary. Then mechanical, with the Industrial Revolution, brought the tractor, which obviously revolutionized farming. In the 50s, people figured out you could actually, kill weeds with chemical, not just, you didn't have to just do it mechanically. Then in the 90s, people started engineering plants to be resistant to weeds, and that was a big innovation that we'll talk a lot about today. We're now in what we call the digital era, and the focus of my talk today is going to take us through what I think are why farming is a great problem to be working on, how we've tackled some of the problems, specifically on weeding at Blue River. I'm going to show you a little bit about that technology and how that works. And then I'm going to set it up for, what's the future look like, and what investments should we be making, and what problems should we be working on in the future to move the needle. couple of graphs down here that I thought were really interesting. This one is the corn yield in the U.S., and you can see that these revolutions are actually really helping with the corn yield, and we need that to keep going to make sure that we solve our problem that I showed on the first view graph. The second one is arable land, and this is a really good illustration of how you can do more with less. So as you get more efficient, you don't need as much land, which is good news. Robotics in agriculture, this is not a new concept at all. You're starting to see some robotic deployments in different areas. So on the one hand, you've got robots that operate in greenhouses doing kind of structured vision tasks in greenhouses. You've got high value crops like I would count grapes and orchards kind of in the high value crop area, where you've got some robotic solutions that are really geared towards those crops. Then you've got drones, which have been active in surveying for quite a while, crop health measurements and weed mapping. Now they're getting into spraying, so that's an interesting development. And then you've also got some innovations in harvesting. So just fairly recently, we figured out how to pick up a strawberry from a vine and not crush it while you're pulling it off. So those innovations are now making it into people's harvesting, especially strawberries. That's one area that's been pretty exciting. So we're seeing robots helping out. They haven't really hit the mainstream yet in a lot of, you see a lot of niche people or first adopters really getting excited about the technology, but haven't yet seen kind of a wide scale deployment. I mentioned in the 90s people figured out how to engineer a plant to be resistant to herbicide. We call this kind of selective herbicides. So the machine that you're looking at right now is a sprayer. It's got a really long boom on it. The ones we use are 120 feet long. And the idea here is that you buy, as a farmer, if you're a farmer, you would buy GMO seed, and you would plant that seed, and then you could spray herbicide on that seed. And you wouldn't actually harm the crop that you're trying to protect. You would only kill the weeds. So this is kind of a dream come true, and certainly in the early 90s when it was introduced, that was true. So we kind of fast forward and look at, we hear a lot about herbicide resistant weeds these days, and it wasn't always a problem, right? So in 1995, there's very few cases. This was right when it was kind of introduced. 10 years later, you saw an uptick. So you're starting to get some more resistant weeds. And fast forward to the kind of like the recent past here. Now you're seeing actually quite a bit of weed resistance, and this is a big problem for farmers. So I wanted to talk about why is it a problem? Okay, so we've got these weeds that are resistant to herbicide. Okay, that means you can't kill them, but what impact does that have? Well, it has a really serious impact on farmers' ability to produce food. So I have a picture of Jeremy Jack. He runs the Silent Shade Planting Company in Belzona, Mississippi. He's holding 2 pigweeds. Okay, pigweed is a type of Palmer amaranth, and a lot of farmers consider this one, public enemy number 1. It's a herbicide-resistant weed, and it's really dangerous to have in your field because of this area right here. This is the seed bank. And if the seed bank, if you allow this escape, when you have a weed that isn't killed, it's called an escape, you allow that to escape and distribute its seeds, you're going to have a huge problem next year. So farmers are really targeting these particular weeds and making sure that they kill them. He's holding 2. The one in this hand is smaller, and this one was actually sprayed by our machine. This other one wasn't. And so you can see the problem is that if you aren't spraying these weeds and you don't have tools to spray them, then your field there's actually a lot of Midwestern farmers, especially smaller ones. They get into a situation where they get a few pigweed escapes, and then the seed bank distributes, and then they have exponentially growing problem as the year goes on, and sometimes they have no choice but to plow their whole field under and try to kill everything. So this is a really big problem for farmers in the field. These herbicide-resistant weeds are worthy of our attention. Our idea is to move from a situation where you treat every plant the same to trying to optimize every plant. I use a metaphor of, like, let's say you have a dorm room and somebody has a cold, but you don't know who has a cold. So what you do is you give kind of everybody, cold medicine. And obviously that's pretty wasteful. It's going to solve your problem, but it's kind of wasteful. What you'd like to do instead is actually make decisions on each plant and give each plant what it needs. And that's really the basis of the system that we've developed. Here's an earlier prototype of our machine. This is a toad array. It's called a toad array, and we have it hooked up to the tractor with a 3-point harness, hydraulic hitch. These white panels here, this is a translucent shroud for illumination purposes. This generation of machine didn't use HDR imaging, so what we had to do was kind of create a lighting environment where we didn't have harsh shadows and we didn't have specular reflections. So that's kind of how this machine works. We've since moved away from this, and we've gotten, the camera technology has improved a lot, and now we can do imaging out in the bright sunlight. So speaking of optimizing every plant, in the weeding case, this is a weed and this is cotton. What you'd like to do is spray the weed, leave the cotton alone. You can also think about, well, hey, I can actually do things to protect the crop too. So I could detect if the crop is healthy and maybe add some nitrogen or add some fertilizer to apply this to the places that need it. You could also maybe detect insects and say, aha, these plants have insects on them, I should apply insecticide to these plants, but these other ones don't, and I don't need to protect them because they don't need it. Fungicide's another one. So maybe, this is especially a problem in hot, humid areas like Brazil. Fungus can get on the plants and kind of start to kill it and reduce the yields. So applying fungicide kind of selectively is a really great idea. And all of these are kind of on our roadmap. The one that we're working on actively right now is the weeding. Here's an example of what can happen if you get overrun by weeds. So a lot of these weeds that you see here are resistant to glyphosate and glufosinate, Roundup and Liberty, and you may have heard of both of those herbicides. So weeding's a really important problem, and as a farmer, you've got to stay on top of it, and it can get out of control immediately on you. Some of these weeds, you might be interested to hear that they can grow up to like a couple inches a day. They're tremendously well engineered to survive in these environments. Here's a picture of how we use machine learning to solve our problems. So we have a crop versus weed delineation system. The green boxes are the crop, and the red boxes are the weeds, and then you can see the numbers in there. This is an earlier prototype. The numbers are confidences. Earlier prototype based on bounding box. We've since moved to semantic segmentation, and I'll show you some of that in a couple of slides. On the far right hand side here, you can see these areas where they're actually sprayed. So we have a precision delivery system that we've developed that can, kind of spray the size of a postage stamp is what we're targeting. Here's a great, kind of a glamour shot, if you will. You've got a cotton plant that's here, and you've got a big, grass weed that's right, and they're both competing for the same resources. Our machine was able to tell the difference between the two and only spray the weed and kind of leave the cotton plant alone. Protect the cotton, kill the weed. Quick video to show you See and Spray in action. This is in cotton in Texas, and so what you'll see here is kind of the view as if you were a plant, getting sprayed by See and Spray. So it'll go by fast, and then it'll go by a little slower. And what we've got is cameras, machine learning, and compute all on board that's doing this in real time. So cameras are taking a picture, we're classifying it, we're mapping it, projecting it to the ground, mapping it to sprayers, and then spraying the area all in milliseconds. So this is kind of some really cool robotics problems, a really interesting marriage of machine learning and robotics and hardware to solve this problem. Kind of an aerial view of this. The green areas show the areas that have been sprayed. So a lot of times we can see like really big savings with this type of machine. 90% for this kind of high precision application, and between 50 to 90 typically with lower precision applications. So three really big benefits, right? You're reducing the cost of your inputs, and that's great because it saves you money. Just to put it in perspective, a farmer who say farms like 5,000 acres of cotton, they actually easily might spend $150K just on herbicide. So if I come to you with a product that I say can put a 90% dent in that, then hey, that's pretty interesting. It's also great for the environment, right? Farmers typically, they don't want to spray more chemical than they have to, and this machine helps them do that. There's also a possibility here, now that you have this precision delivery system, maybe you can actually switch to conventional seeds. They're cheaper, and that might be an advantage because it actually reduces your inputs. But it's only an advantage when you have a precision machine like this, because with non-selective herbicides, these are herbicides where it will actually kill the crop and the weed, not just the weed. You need this precision delivery device. So this tool kind of unlocks a couple of really interesting and good for the environment, saving money and reducing your input costs. So the other thing is you can actually fight resistant weeds with this using non-selective herbicides. So there are herbicides out there that nothing is actually the weeds are not resistant to, and they won't become resistant to. But it's too expensive to spray, broadcast over your field, and if you did, you'd kill your crop. So obviously you can't do that. But with this precision delivery device, you can start to unlock that fighting the weed resistance. Wanted to share something really cool with you. This is what we call an as-applied map. So we're testing our machines out this summer with customers. And in previous seasons, we've sort of showed up at customers' fields and said, hey, we'd like to weed your field for free, and you give us feedback. And obviously they're quite excited about free weeding. So we get a lot of participation in that program. This year we said, hey, we want to actually give you the keys to the sprayer and have you operate it and you run it, and then we'll kind of interview you afterwards and gather feedback for how how did the machine do, what was good, what was bad, and we can use that in our improvement cycle. The map that you're looking at here is what we call an as-applied rate map. So the color scheme is gray means no herbicide was applied, and orange and green mean maximum herbicide was applied. So the thing to compare this to is if you were doing broadcast, the entire thing would be orange. You can see that with our seam spray machine, the entire thing isn't orange, and you're getting actually like pretty high savings on this particular field. So it's interesting to watch there's a lot more weeds in this area. That's why you're getting a lot of spray. A lot fewer weeds in this area, and you're actually saving a lot of money. So the whole idea behind this machine is let's reduce your inputs, but keep you at a very high rate of weed kill so that you can keep your yields up. That's what it's all about. Another interesting example, I was out in the field last week, and I participated in this study in Iowa. Here's a field that had really high weed pressure in the south part of the field, and then lower weed pressure at the top of the field. And what's interesting about this is, if you have a high weed pressure field, you might say, well, I'm not really going to get a benefit from See and Spray in this field, and you're kind of partially right. If your whole field is really dense weeds, you aren't going to see a big savings. But this field and a lot of fields like this have a distribution of weeds where it might be pretty dense in one area and less dense in other areas. And then even in this very weedy field, you can save 30%. So those are real numbers to farmers, and even in these situations where you think it's maybe not a super great fit for our product, you can still save significant amounts of money and materials. I'm going to shift gears now and talk about some of the computer vision challenges that we faced and how we've solved them. So our farmers can really operate, any time from dawn to dusk and all times in between. The images look a lot different. If you're in the morning, in the early morning, you've got like a pretty warm color temperature, and at noon you've got a pretty cold color temperature, and all gradations in between. So our early models actually didn't really account for this, and we found that as soon as we got outside of our kind of narrow training window of, say, 10 a.m. to 4 p.m., that our performance actually wasn't very good. So we found that augmentations actually really help us, and we had to go beyond the kind of normal augmentations that you'd learn about if you're working with ImageNet or something like that. You've got kind of the standard ones, the flips, rotations, mirrors. But in the real world, right, we have color temperature, which is a big problem. We've got sensor noise, blur, dust, and brightness. So we were able to augment. What we do is we use ImageAug to do most of our augmentations using PyTorch. And we found like a set of augmentations, including ones that we've developed, have really helped our model. So our augmented model now is actually really stable over a much wider range than a non-augmented model. Dust is a big problem for us. So farmers like to drive fast. And when you drive fast on a dusty, on soil, you create dust. Dust obscures what you can see in the images, and that affects the machine learning model performance. So dust is a hard one because normally what you do is if you found an area where you needed to change your performance, you'd say, okay, I'm going to go get some training data, get some labels, throw it in, and then fix the problem, right? But with dust, actually, you can't do that because it turns out humans can't label the dusty images either if they're too dusty. They can't tell which is plant and which is weed, and they make mistakes. So you end up getting this noisy, dusty signal, with noisy labels into your machine learning model, and that's not how you want to solve this problem. So what we did was that we actually developed a dust augmentation that helps us solve this problem. Now, it doesn't solve it, as you can see, the difference between the blue graph and the orange graph. We haven't solved the problem completely, but we've made it a lot less worse than it was. So just show you a little GIF of this. On the left-hand side, it's actually the same scene at both, and you've got a model with no augmentation and then a model with augmentation. And what we've got here is, this is our test site in Gilroy. I've got a camera pointing down at these images and at these weeds, and then we've got a fog machine to kind of simulate dust. So red is weed and green is crop. And you can see as the fog moves into the non-augmented model, kind of everything turns into crop with a high confidence, and that's a disaster because if we were to release this kind of a model, then as soon as the machine encountered dust, which is very often, by the way, the machine would stop spraying. The customers would be really unhappy with that. So what we've done is we've actually augmented the model. You can see it's much better on the right-hand side. Not perfect, but a big improvement. The other kind of improvement that we've made here is really trying to figure out when we're in a dusty situation and when we're not. So the takeaway from this graph is that the machine learning model makes really high confidence predictions that are completely wrong when it's out of its domain. And so the way that we've handled this, there's actually some research on this too that was recently released by, I think it was DeepMind, but models will be confidently incorrect when they're faced with new situations they haven't seen. So the way we handle this is we actually have built detectors in our machine learning model to detect the probability that the image has dust, has low light, and is blurry. So that allows us to make sure that we don't, if we're in a regime where we don't think we trust the model, then we can take other actions, like we can say, I'm going to turn the sprayer on because I'm in a dusty area and I'm not sure my machine learning model is working. So you can see this in here. That first number on this left-hand panel is dust probability. So when there's no dust, the probability is pretty low, and when there's high dust, the probability goes high. So that allows us to trigger into this what we call a fallback mode. And same idea for the other low light and blur. We've been working with synthetic data recently too, and I thought I'd show you some examples of that. This study's ongoing. We haven't made any firm conclusions on it, but I wanted to show you kind of where we're at with it. When I first posted these on our Slack channel, it was interesting because people say, hey, what field is that? I don't recognize that one. And is this Arkansas? Is this Mississippi? Like, where was this taken? And it fooled, actually, almost everybody who looked at it, because the quality of the modeling, the quality of the plant models and the shadows and the backgrounds, is actually really, really high. So we're starting to use this to help solve problems that we have. And so some of the problems that we have, typically when you have a model that you want to improve, your strategy is, okay, I'm going to go select training data, get training data for that, get it labeled, get it into the model, and then try to improve my performance that way. But there's a lot of problems where it's actually really hard to do that. So, example, our models need to be able to detect weeds in the row or between the rows, and the weed can really grow anywhere. So we need to improve our model has to be really good at detecting weeds in the row, which is a really hard problem because some of these weeds actually look like the crops we're trying to detect. So what we've done actually is contracted with a synthetic data company to generate these scenarios that are hard for us. And one of the scenarios that we've done is weeds in the row line. So I'm going to show you a couple of examples of this, but the top left frame here, this shows the picture, and there's a great big weed right here. So you've got this is cotton, and then you've got a great big weed that's right in the row. It looks a lot like a cotton plant, and this is actually pretty hard for the model to pick out. So here's an example of kind of our non-synthetic model. It's picking out a little bit, but you can see that there's actually a lot of areas that are missing of the weed. So when you just do synthetic data, right, obviously the result isn't very good, and you'd never be happy with this. And this is primarily because of the domain gap. Synthetic data still has a domain gap from real data. That's an active research problem, but you can still get value from it. And what you do is you add data and you train for longer. So these 10, 50, 100, 150, these are epochs that we train. So we would transfer, learn, and then train and fine tune on our real data. And so what we see here is that the synthetic data is actually the model trained from synthetic data with real data as well is better than the one just trained with real data. So this is super exciting for us, and we're excited by the possibilities of using synthetic data to augment our training. It's never going to replace real data, of course, but we think there's a lot of potential here and a lot of ability to specifically model scenarios which are hard. A couple of graphs here. The x-axis just shows you the epoch, and again, so, just using synthetic is very bad compared to the real models. But as you add more and more synthetic, and you're increasing your number of epochs that you're training, you're actually starting to get some material improvements, especially in some fields. So these little dots here in this variance is on a per field basis. So we're seeing improvement in some field, even though it doesn't look like there's a lot of improvement on the aggregate. We are seeing substantial improvement in some of the fields. So this is a work in progress, still evaluating, but so far it looks pretty exciting from our perspective. All right, I'm going to round the home stretch here. What are some problems that I think are really interested in the future? Silicon Valley folks like to think of things as a software stack. So what does the farming stack look like? Well, it looks like preparing your soil, tillage, establishing the stand is planting, fertilize and irrigate, protect, that's where we come in with weeding, that's our starting point, harvesting, and then learn and optimize for the next cycle. Where we want to get to is putting smart machines in each of these, operating each of these layers, and driving improvements in each of these layers. And we believe there's a virtuous cycle that develops from this, where even sort of marginal improvements in each thing will actually have an overall large improvement when you scale them out to sort of thousands and thousands of farmers across the US and Europe and Brazil and really globally. So we think there's a tremendous opportunity here to, going back to kind of the challenge of solving farming, we think there's a tremendous opportunity to improve each layer of the stack here, and then learn and optimize and keep improving those things as time goes on. Smart machines really operate in the overlap area of sense and decide, act, and verify and learn. In order to be successful, you've got to really understand how the job is done, and nothing is better than spending time with farmers to understand this. And that's what we spend a lot of our time on at Blue River, is hanging out with farmers in their fields, really trying to gain empathy for the problems that they're having and how they're solving them today. We have to understand what sensors are needed, how to verify when things are done correctly, and kind of what's the downstream impact. You don't want to spend your time optimizing something that has a low impact on the back end, right? You want to understand what the impact is of everything you're looking at and pick the one that has the biggest impact and tackle that one first. So a good understanding of that whole stack is really critical. All right, time for bold prediction. Our kind of bold prediction for today is that autonomous farming equipment is probably going to hit before we see significant adoption of autonomous cars. Why? It's a constrained environment in ag. There's a lot of repetition. You have no penalty for stopping. If you're having an autonomous tractor and a person walks out in front of it, you could just stop, and that's no big deal. That doesn't work on a freeway, right? That's a disaster. So a lot of different problems that you have to solve. The speeds are lower, and there's a need because there's a lot of labor shortages. It's really, really hard for farmers to hire people to help them with their operations. So autonomy is a really attractive thing. Leave you with a picture that's really exciting. This is a project that we're working on. It's an autonomous sprayer. We rolled this out at Agritech recently, and this is in development right now. It's in front of customers this year. We're getting feedback. The idea is that this guy can enter your field. It only, because of the tracks and the lightweight compared to a large sprayer, it can enter the field when it's wet. And this is an autonomous machine that can see and spray. So imagine kind of a fleet or several of these things running through your field in an autonomous fashion, able to enter the field when it's wet, which is quite a big improvement over our current generation of sprayers, which if you took them into the field when it's wet, you'd have a chance of getting stuck and compacting your soil and reducing your yields. So this is super exciting. I think the future, there's a lot of opportunity for innovation in the ag space with robotics and machine learning. And in my opinion, we need our best and brightest minds working on this problem. It's a very impactful problem, and it's going to make a big difference for us as stewards of the land. So I'm really excited about this problem, as you can probably tell, and I'm happy to answer any questions in the follow-up session about this. So thank you so much. This is a picture of our team. Really excited, motivated group of people. We're located in Sunnyvale, and it's just been really a lot of fun working with this team and working on these problems. So with that, I'll leave you and enjoy the rest of the conference. Thank you so much.